Hi, my name is Lori Williams. I'm a distinguished professor at North Carolina State University, and it's my pleasure today to be talking to you about secure development lifecycle. Just some acknowledgement to the University of Bristol and the Cybersecurity Body of Knowledge project. And we'll go ahead and get started. Security software lifecycle, that's the subject, and I want to distinguish, what is the subject versus other aspects of the software engineering aspects of security. So a security software lifecycle is a comprehensive approach for the whole software lifecycle and looking at how do we add steps or change steps to prevent and detect all classes of security vulnerabilities and security defects. And so this is different than just saying, like, you could have a whole body of knowledge around security requirements or security testing. But really what this is about is the whole life cycle and aspects of projects that have been done that really look at the entire life cycle as opposed to just fixating on one practice. So what we're going to be talking today about is first the history, so what has led us to the need for a security development lifecycle. And then we will go into 3 specific prescriptive secure software lifecycle processes. And prescriptive meaning there are recommendations about what you should do. Then we'll talk about some specific adaptations of these secure software lifecycle models for some modern contexts. And then finally, assessing the secure development lifecycle. So if you are a team and you are doing a secure development lifecycle, how do you know, like, some measure of how are you doing? All right, to start out, history. And I say history, but unfortunately for the world, it's not only just history. Currently, there's a lot of organizations that are still in this model, and this model is called penetrate and patch. So what is penetrate and patch? And so penetrate and patch is really where the security of an application is assessed when the product is complete. It could be that the product is complete and then you're doing penetration testing, which is testing from the outside on a complete product within an organization before it's released, and then fixing it at that point. The other penetrate and patch means an attacker actually penetrated your application and now you're rushing to try to fix it. But the main thing for penetration and patch is the product is complete. So if you find a vulnerability at that point, there's several downsides. One is very costly to fix. We've known from the software engineering economics for quite a long time that when you find a defect late in the process, it's orders of magnitude more expensive to fix than if you found or prevented the vulnerability or defect in the first place. And that holds with vulnerabilities as well. Another downside of this penetrate and patch model is that attackers can find and exploit vulnerabilities without being noticed. So if you put products out that have more vulnerabilities, they can find and exploit the product and sometimes actually be doing it unnoticed. I mean, there are studies that say that it can take months and sometimes even towards years of a product being actively under attack and no one noticing that that's the case. And so, someone has access to a system and no one even knows they have access to the system. So that's a problem. And then the third downside is patches can introduce new vulnerabilities and other defects. And I say urgent there because a lot of times when there is a security vulnerability that is detected, then the whole team rushes to fix it. And in that rushing, the quality of the patch can be less than it needs to be. Then it introduces a new vulnerability. And then the last one is patches often go unapplied by customers. Even though increasingly products like operating systems and mobile applications have auto update processes where we should get security vulnerabilities fixed, There are lots and lots of users that don't apply patches, and that enables attackers to attack. An example here over on the right is the WannaCry vulnerability that was detected a couple years ago. It was a ransomware type of situation, and Microsoft had actually fixed the vulnerability that was exploited, but because attackers know that often customers don't install the patch, then they use that opening and and used it for their advantage for the ransomware attack. So the fix was out there, but we provide information to the attackers on what they should exploit once the knowledge of the vulnerability is out there. So all of these say penetration patch, not a great strategy. And so this was back in 1998. Gary McGraw, whose picture is kind of in the background there, in 1998, there wasn't a lot of information about marrying software engineering and security together. And so in 1998, DARPA funded a project for Gary to focus on the application of software engineering to the assessment of security vulnerabilities. And so that was really the first initial work, that the term penetration patch came out of that. And Gary, with a colleague, John Viega, advocated for proactive and rigorous software analysis to assess and prevent vulnerabilities. And they went on to publish the first book, Building Secure Software, in 2002, or I think it was 2002, where really it was the beginning of bringing software engineering into security. A little bit after that, Microsoft found itself sort of in a mess where their reputation for having security vulnerability was getting worse. And so Bill Gates in 2002 announced the Trustworthy Computing Initiative. And so basically what he did was he stopped a release of Windows that was planned and said, we are not going to release again until we have a high-quality product. And he announced this Trustworthy Computing Initiative. And then lots of people in the company really joined together and had the mission of developing secure products. And they authored software security development lifecycle, used it within Microsoft, and then by 2004 were ready to contribute their processes to the community. And so even today, and as we'll talk about, Microsoft has resources for secure development lifecycle. And a key was what Bill Gates said, and the quote is at the bottom here: trustworthy computing is the highest priority for all the work we do. We must lead the industry to a whole new level of trustworthiness in computing. And so he set the stage, at that point when he made this public pronouncement, sent out this memo about trustworthy computing, stopped the release, sent a very strong message to those in Microsoft and in the industry as well. So between McGraw, Viega, and Microsoft, often running with the marriage of software engineering and security. From that, there was a number of different prescriptive lifecycle processes that were authored, and I'll be talking about 3 of them today. The first one is Microsoft Security Development Lifecycle. It has 12 practices, and we'll get to the others that have a few less practices, but all 3 of these, very popular in the industry, lots of resources available, and especially the thing is that they are comprehensive, so they span the whole life cycle and not really fixated on just one area. So Microsoft does have 12 steps to their life cycle, and up at the top of the screen are all 12 steps. Maybe hard to read them, the wording in those 12 steps, but we'll be stepping through them. And the first step in their process is to provide training. So just acknowledging that a lot of people in the industry at that time and currently don't have knowledge on how to develop secure products. And so there is a need for an organization to have a training offering for their personnel, and really comprehensively covering all of the aspects of the secure development lifecycle, design, development, test, and make sure that lots of people are trained. For example, 80% of all the technical personnel are trained, and then also have this training on a cadence where you don't just take this one time and think that now you're a security expert. The target is always moving. The attackers are getting smarter and more aggressive every day. They're coming up with new techniques. And so the training has to needs to keep up with what are the trends of what attackers are doing and providing that information. The next step in the Microsoft process are security requirements. And the key there is that you need to consider security at the start of the project. So when the team is coming up with their requirements, which are often functional requirement based, to make sure that what needs to be done for security is in there at the same time. And that can be ranging from creating a feature specifically to make the product more secure. And it also just means making every functional requirement more secure. And so you need to define those at the beginning of a project. Some specific things to bring in are the security implications of a functional requirement. So if you look at a functional requirement, meaning this is something that the user wants, some functionality within the system, and if you look at that functionality, what are the implications of that from a security context? And so, just as an example, you could have a medical records application, and there's a new requirement that allows the nurse to edit a patient record. That's a new requirement. And so from a functional standpoint, it may just say, as a nurse, I'd like to be able to edit patient records so I can offload some of the work from the doctor. And that's a functional requirement, and software engineers know how to handle that. But from a security standpoint, the implications are the nurse needs to be logged in, the transactions need to be logged, so that you make sure that you understand who updated what patient record. Some parts of the patient record need to be encrypted. So you take a functional requirement and there is a mapping to the security implications that need to be considered, and so all of that needs to be in the security requirements. There are legal and industry compliance standards, and we'll talk about compliance standards more, but say something like HIPAA, HIPAA is for healthcare applications, and so a healthcare application needs to be HIPAA compliant. And so if you look at HIPAA, what you'll find there are some functionalities and some standards that need to be implemented in order for this application to be HIPAA compliant. Those go into the security requirements. I'm also thinking about known threats, previous security instances. So all of that funnels into the fact that you need to have your security requirements set. There are some techniques for systematically developing security requirements. Square is one. It's a process out of Carnegie Mellon. Abuse cases, which we'll talk about, ISTAR, chaos, these are all systematic means of identifying the security requirements that would be good for a team to use. Next process in the Microsoft is defining metrics and compliance reporting. And so with that, like Lord Kelvin says, if you can't measure it, you can't improve it. So it's really a good idea to have some measurements around security and how you're doing. Microsoft calls this a bug bar. So the bug bar is really saying, how many vulnerabilities can we be working on at the same time? How do we handle moderate, important, critical vulnerabilities? So like measures around, the bugs and fixing the bugs that are reported. Compliance reporting, like, knowing that what are the standards that you need to be compliant with, and what do you need to record in order to be compliant, having that acknowledgement. Next one is to perform threat modeling. So threat modeling is a process that the team can use to understand security threats to a system, determine the risks for the threats, and establish appropriate mitigations. And so what a team generally will do for threat modeling is develop an architecture diagram or a data flow diagram for their system, and this is done early. So it's done, after the requirements are in place, but before you really have set off on a lot of implementation. And also, like I'll say, this looks like a timeline, but it can be done iteratively as well. So this is the diagram part. So you have an architecture diagram, a data flow diagram, and then the team collaboratively comes together and enumerates all the threats, all the different things that people can do from the outside for that architecture, and then enumerates them, decides how to mitigate those threats, and then validate that you actually have done that. So it does start with this diagram, and then many teams use what's called the Microsoft STRIDE model. STRIDE, the S stands for spoofing, the T stands for tampering, the R stands for repudiation, the I is information disclosure, D is denial of service, and E is elevation of privilege. And those 6 types of threats in the STRIDE model are orthogonal. They're different from each other and pretty comprehensive. So what a team will do is look at this architectural diagram and maybe focus on the S first, the spoofing. And they'll think all of the different ways and all of the different user types of the system. How could someone spoof? And collaboratively, everybody looking at that. And then close up any gaps that you may have. And then move on to tampering. How can you tamper? So that's all threat modeling, trying to close up all the gaps at a high level before moving on. There are some games that can be used for brainstorming threat modeling. Elevation of Privilege is a game out of Microsoft, a card game. There are other, there's a game called Security Cards, and I will say myself, I did come up with a technique called Protection Poker, which is a game, if you will, that the team can use in order to perform threat modeling in a creative way. Number 5 for Microsoft is establish design requirements. And so, now you're getting into the system design. There are a number of design principles that have been authored over the years. And so as you're designing the system, you want to make sure that you are up with making, the secure design. So some standards that have been put in place. So Salzer and Schroeder in 1975 came up with a number of design principles. John Viega and Gary McGraw came up with some design principles in 2002. Also in 2014, there's an IEEE Center for Secure Design that enumerated the top 10 security design flaws and the design principles that you need to consider because of those. And so there are some of them. This is a subset that are on the slide. Economy of mechanism, making sure that you keep the design of the system as simple and small as possible so that it's less complex. Fail-safe defaults. You want to base your access decisions on permissions rather than exclusions. You want the default to be lack of access and the protection scheme to identify conditions of when an access should be allowed. Complete mediation says that every access to every object needs to be checked for authorization so that, once you're in the system, your access control is continuously being checked to make sure that you still have the access that you need for the privilege that you're trying to access. Least privilege, every program and every user should operate using the least set of privileges necessary to complete the job, to contain the exposure. Least common mechanism, minimize the amount of mechanisms common to more than one user and depended upon by all users, so you can kind of separate out who gets what and watch for the overlap between them. Defense in depth, multiple layers of security controls have to provide redundancy in the event of a security breach, so that if the attacker passes through one layer, there's another layer of protection there. And so the attacker, to be successful, may need to navigate through several layers if you have a defense in depth strategy. Next principle, give or earn but never assume trust. So you want to, by default, deny people access rather than give them access. And then last, always consider the users. So we can make a system so secure that people, users, will find a way around them, around your protections, and then ultimately be worse in the long run. For example, there was a study out of Cornell, and in that study there were doctors, and there was a concern that doctors would walk away from their computers when they went into patient rooms in the hospital. And so what they devised was a mechanism where when the doctors got too far away from the computer, they would get logged out. And the doctors didn't like that because they kept coming back into the hallway and re-logging in. So they determined that if they put a styrofoam cup over the sensor, then the computer would never know that they actually had walked away. So ultimately, they made the situation worse. So as we come up with our security mechanisms, we need to make sure that we aren't creating such a psychological barrier, making the workflow of the users so much worse that they find an insecure way around our protections. Practice number 6 from Microsoft is define and use cryptography standards. And so cryptography is a way to protect especially sensitive information, and you're protecting the confidentiality of the data, unauthorized modification, and the key with cryptography is that there are known cryptography algorithms and known protections and known standards, and the very best idea is to get an expert to work on how you're going to use cryptography and for the whole team to work together and use the same standards. You would never want to have someone try to create their own cryptographic algorithm. Better to use industry standards and for the whole team together to choose out what you're going to use. Number 7, manage the security risk of using third-party components. So in today's day and age, everyone is using third-party components, open source components. So they're using libraries and different algorithms that come from an open source or external third-party location. And there are risks associated with that because those were not developed during your own development process, and using your own standards and your own testing techniques and done by people that you trust. And so there's a lot of risk associated with that, and it's something that the team needs to really consider in their choices and how they have trust boundaries in their design based upon these components. What this slide is here is saying that the open source vulnerabilities published per year, and you can see that more and more vulnerabilities are being published or being discovered in these open source components. And there are now tools. OWASP has a tool called Dependency Check. There's Black Duck software. There are people who are developing tools which you can run on your system, and it will find your dependencies on these external components and tell you if any of those components have published vulnerabilities, meaning that you should get a new version that closes up that vulnerability. The only thing is that it really is still an intractable problem, that these components get vulnerabilities all the time, and so you could spend your whole life just updating your components and not making any progress. And every time you take a new version of component, there needs to be a testing effort. Sometimes the API will change. And so it's still a difficult problem, but it's important that you have an inventory of the third-party components you use, and you keep up with the vulnerabilities that are in them. Next step is use approved tools. So an organization should have approved set of compilers. We'll talk about static analysis, debuggers, dynamic analysis, the IDE, and so the team should have approved tools. Those tools should have settings that are set so that it's as secure as possible, and that you also are always looking at, are these the right tools, or do we need to change our settings? Okay, number 9, perform static analysis security testing. And so static analysis, these are tools that you can run in your code, and they look for bug patterns. Static analysis tools have been around for a while, but more recently they also specifically have bug patterns that are focused on security and will enable the team to find security vulnerabilities. And so they look at the code statically. They're not running the code. It's not dynamic analysis, and identifying bug patterns and notifying the team. And so then the team members can look at the tool and find the lines and find the offending statements. The good of it is it's a way to find your vulnerabilities, some of them anyway. The bad of it is these tools can have false positives. And so as a developer, you're looking at the messages and maybe declaring that some of them you don't want to fix. So it can be overwhelming sorting through what you want to fix and what you don't want to fix, but the tools are very valuable. Next is perform dynamic analysis security testing. And so this is where, dynamic analysis means the code is running. It's been compiled and it's actually running, and tools can look at and run test cases, automatically generate test cases that run from the outside, like a black box. One of the techniques for dynamic analysis is called fuzzing. And fuzzing is when the tool knows how to create a myriad, a large set of different malformed inputs. They know, the tool understands how to act like it's an attacker from the outside, and to just keep stuffing all of that bad formed input into the application. This is a little comic here. It says the #1 programmer excuse for legitimately slacking off, and it says my code is fuzzing. And so what that really is saying, it used to be compiling, but compiling and building is becoming more efficient these days. Fuzzing does take a while. So when it's really best if you're going to fuzz your code to do it overnight, or to do it as you're going to head off for lunch, because these tools generally will run and run and run, finding all of the ways into your code. Number 11, perform penetration testing. So penetration testing is humans looking at the code, looking at it opportunistically, thinking about how could they break in based upon their knowledge of what attackers do. Important step, but it's important to do all of the other steps. The penetration patch are organizations that really the only thing they do is this perform penetration testing. So they develop normally, if you will, and then they have someone who does this type of penetration testing, but it's really just too late at that point. And then the final Microsoft step, establish a standard incident response practice. And that really the issue here is that no matter how much preparation you have and you take, vulnerabilities, the attackers are always doing brand new things, zero-day attacks, unexpected things, and so you really do need to have your system, your organization set up that when something does happen, you have a process of how to contain it, how to fix it, how to get the fix out to the customers, just how to handle the situation so you're not caught off guard. Okay. So that is the end of the Microsoft 12 practices. The next thing we'll talk about are the touch points. There are 7 practices. The touch points were defined in a book that Gary McGraw wrote called Building Secure Software. And in the book, like, he does talk about, one of the concepts he talks about are design flaws versus implementation bugs. Design flaws being big systemic problems with a product that create vulnerabilities. Implementation bugs are small lines of code that are vulnerabilities, easier to fix because they're small lines of code. All right, so up at the top are different steps that are taken within touch points, so different security practices, and they're actually put on this slide in the order of priority based upon Gary McGraw's experience. And at the top, so that the diagram there is really showing where in the development process these practices come out. And also, it's not a waterfall. All of these are done quite iteratively. Up at the top of the 7 steps, there is a lot of overlap between what I talked about with Microsoft. So I won't repeat it. There's only 3 that are really different than the Microsoft, and so I'll only be speaking about those 3. Up at the top, just to summarize, there are code review tools that translate to the use of static analysis tools. So the static analysis tools are doing a code review, they're just doing it automatically. Architectural risk analysis, which is the second one, is very similar to threat modeling, which we discussed. Penetration testing we talked about, and security requirements we talked about. So I will just go through the remaining 3. First one, risk-based security testing. And so what this is saying is, based upon the findings that you have, fold that information of what you learned into testing, planned out security testing. So up at the top, that's threat modeling. So based upon your threat model, write some specific security tests. And then the bottom is based upon your penetration testing, then plan out additional test cases. So based upon the information you're finding, then formulate the rest of your test cases. And that's based upon risk. Another is specifically abuse cases, and abuse cases are a form of security requirements, and use cases have been used in the software industry for quite some time. This is a diagram, and in that diagram, there on the left side are the good users of a system, and on the right side are the bad users. And so in a use case diagram, you have the good users and what they want to do, and that's normal. What abuse cases bring in is you're looking at what the bad guys want to do. And so, like in this case, you have a rogue employee who wants to sabotage. And so, what you do when you develop abuse cases is you think about who are all the bad actors, who are all the people who actually want to break into the system, and what do they want to do. And those are the use cases or abuse cases that are in the black circle. And then you tie together the use cases and abuse cases, thinking about how does this particular abuse case threaten one of the uses, and how can we mitigate that. And so what you're laying out here is all who are the bad guys, what do they want to do, and how do we stop them from doing it, and plan that functionality in at the start of the process. And then the last one, security operations, is the number 7. And the idea really for security operations is when attacks actually do happen, then you want to feed back the information of what happened throughout the whole process. So that is brought out with the security operations practice. So that's really the end of the touch points and the unique aspects of touch points that did not show up in the Microsoft Security Development Lifecycle. And we'll go on now to SafeCode that has 8 practices. Okay, so on this slide we talk about the third secure software process. It's called SafeCode. SafeCode is actually an organization of companies, and on this slide are the charter members of SafeCode. So these companies, there are more companies now as part of the organization, but the mission of SafeCode is to together produce documentation for practices that can be used by others in order to develop secure software. And so they, up at the top of the slide, are 8 practices that are in their process. Most of them we've actually talked about when we talked about the Microsoft Secure Development Lifecycle and the touch points. Only 2 of them are unique. But if you look across the top, some may not look as familiar. So security controls is their way of saying security requirements, and we've talked about that. We've talked about design. Secure coding is one of the unique processes or practices for SafeCode, and we'll talk about that on the next slide. Third party is what we've discussed about before, like in the secure development lifecycle, it was called managed security risk of third-party applications, so that's an overlap. Security testing we've talked about. Security findings is really just managing all of the findings from the prior practices and keeping track of them. Security response or vulnerability response is similar to incident response in prior practices related to security operations. And then lastly, the deploy secure development lifecycle is unique. So we will just talk about the 2 unique ones now. The first one being secure coding practices. And so there are lots of language lists out that are available of the language constructs that should be avoided in order to have secure software. And so that practice is really pointing you towards some standards that you should use in order to have the actual lines of code using safe operations. And then the other unique one is the planning and deployment of a secure development lifecycle. And that's really taking all of this and bringing it out into an organization. And bringing it out to an organization involves training, which was gone over in the Microsoft Secure Development Lifecycle. So it does involve training, but it also involves organizational management type of practices to spread the culture, spread the practices and the culture, and change management systems in order for the organization to adopt the use of the secure software lifecycle. All right, so that is the end of these comprehensive processes. There are a number of adaptations kind of in specific domains that have come out, and I'm not going to go through the specifics of all of those, but you can see here there's a number of different adaptations, and I'll give you some highlights of those. So the first being Agile. So Agile and now Devops or continuous deployment, very rapid deployment of software. How does that change the security development lifecycle? SafeCode came out with some security user stories, and so there are resources there that can be used in order to use, to work in an Agile context. Also, Microsoft came out with its secure Devops, and the highlights of their additions for the secure Devops is, one is keeping credentials safe. There's a lot of rapid deployment with Devops, and so making sure that you don't put things like passwords in your deployment scripts. And then continuous learning and monitoring. There's a lot of instrumentation that goes on with Devops. There may be feature experimentation where they're trying to instrument to see if customers actually like the new functionality. And so learning from that all the time is something that's in the Microsoft Secure DevOps standard. Mobile, there are some specific OWASP resources for secure testing and threat modeling in a mobile context. that we could take a look at. Cloud. SafeCode has some practices for cloud that can be instituted into a development lifecycle, specifically, related to some cloud-based security threats. Things like multi-tenancy, tokenization of sensitive data, having trusted computing tools, data encryption and key management, things like that relate specifically to cloud. Internet of Things is getting more and more popular and more pervasive within our world. And so NIST came up with some standards, and what they're really talking about in their standards related to Internet of Things and security is things like use of our RFID or radio frequency identifier tags on the things, if you will, and also not allowing default passwords. There have been denial of service. There's a big denial of service when the default passwords of mobile or of video cameras were compromised in the Mariah threat, so not allowing that in development, using manufacturer usage descriptions or MUD descriptions to specify authorized and expected user traffic patterns, having a secure update process so that if one of the devices does get compromised, there's a way to update it. Sometimes the devices can be so small that there's no way to update it, and that's a problem. Road vehicles, there's a number of standards, particularly the U.S. Highway Traffic Safety Administration has provided some guidelines, and specifically looking at, because a road vehicle is a system, it's not just software, so you're working with hardware and software, so how do you work together in the system? What should your requirements look like to have a secure road vehicle system? And then finally, the e-commerce payment card industry, PCI, they have a data security standard, and it really provides some strict guidelines on encryption and use of antivirus software and testing and whatnot in the payment card industry and how that folds into the secure development lifecycle. All right, finally, assessing the secure development lifecycle process. So just say now you are an organization, you've tried to institute some of these practices and/or you plan to. How do you look and assess your overall progress? So we'll talk about 3 different assessment vehicles. One is the OpenSAM framework, and SAM is Security Assurance Maturity Model. And if you look at this framework here, there's 4 different functions: governance, construction, verification, and operations. And each of those are broken down into a number of processes. And what the OpenSAM does is lay out more than 100 practices that fall into these categories. And then the team can assess their use of those practices. They can create a roadmap of where do they want to go with each of these practices. And if you look up this OpenSAM framework, there's Excel spreadsheets and that all work together in order to provide an organization with a good picture of how they're doing with their implementation progress. And those, you can use the SAM assessments on your own organization. You can hire a consultant that will do the assessment for you, but the bottom line is you can graphically look at how are you doing and where are you going with your security lifecycle practice. From OpenSAM came a more proprietary practice called BSIM, which is the Building Security and Maturity Model. And it has, it has 12 practices, which are on the screen here, that occur in 4 different domains. And then under each are specific activities that a team does. It's 113 of them. The way that BSIM, so BSIM and OpenSAM are structured quite similarly. And actually, it's because BSIM originated from OpenSAM before it forked off. But the difference is that the BSIM is done through proprietary body. It started out being Cigital, which is Gary McGraw's company, which was sold to Synopsys. They come in and they work with the team, and they don't just say, you know, do you do threat models? They're like, show us your threat model. And they do an assessment of how the team is doing based upon that. And then what they do, this is a Earth spider chart. So in each of those different practices, it will tell you how you're doing. So it'll graphically display how you're doing on all of those different dimensions. And then for your domain, you'll also get a comparison of how you're doing versus how other people are doing. So like the advantage of BSIM over SAM or OpenSAM is that you have this external assessment. You know, you really have to prove where you are, and then you get a comparison to others in your domain. And then the last assessment vehicle is the common criteria. The common criteria is an international recognition of secure information technology, secure IT. And so what you do with the common criteria is have a comparison between the results of an independent security evaluation based upon common requirements for secure functionality. And what it does is establishes a level of confidence in the security posture of the system and helps consumers determine whether the IT product fulfills their needs. So it's an internationally recognized standard. And so for some organizations, depending upon their criticality, they may need to have, you know, a certain level of common criteria in their vendors. And these are the different levels. Starts out with, at the lowest, EAL1, functionally tested, which means mainly functionally tested, not as much security analysis, security threats tested. You know, and it goes up with the level of testing and focus on security at the different levels. Up at the highest, ELA7, formally verified, tested, and designed, which means that when the system is extremely high risk and the value of the assets justify higher costs related to formally verifying testing and design. So, and then you have this, you know, externally recognizable level from the common criteria, which again, depending upon the context, may be something that an organization needs to prove in order to perform service or a product for somebody else. All right, to summarize, you know, it's important for an organization in today's day and age where attacks happen every day, they're in the news every day, and nobody wants to be in the news. So it's important for an organization to have a comprehensive secure software lifecycle. And organizations, even though I gave you some prescriptive lifecycle models, it's important for an organization to customize their own and pick and choose the practices that they want to do in order for the culture to embrace the need for these practices and to develop a secure product depending upon the criticality of the product. And it's important to really consider the cultural change that needs to be taking place in order for a team to consider security throughout the lifecycle process. All right, well, hopefully you got lots of good information about that and more in the chapter. Thank you for your attention. Bye-bye.